Hi again. I hope you're doing well. So in today's class, we're gonna continue with Turing complete from where we left in our previous class. And yeah. So in the previous class, we studied uh, about basic gates. Like we have this gate which is we have a NOT gate, which is an inverter. We have an OR gate, which looks like this, and we have an AND gate. These are the most basic gates that we have, and in this we were able to start with an AND gate, and yeah, we did start with an AND gate, which can be made from this, and using this NAND gate, it's a special gate called a universal gate, which means it can be able to create any kinds of other kinds of gates rather. We also did a NOT gate, which is same as this. We also did an AND gate, which is this. We also did an OR gate. Yep, we did this. We implemented this, and we also had something new, which is an OR gate, which is just an OR gate, but with this circle thing, which means the signal is inverted. And let's see what we have today. So in today's class, okay, let's say it's always on top, but let's see what the level is about. So it says create a circuit that is always on. This should be easy. We need to create a circuit that is always on. Okay. So it means regardless of the input, the output should be on, I guess. Okay, so in that case, if we just connect a simple wire and input is on, this is the input, this turns on this, and you can't control the output since it's controlled by whatever is happening. I don't know what happened over here, but yeah, this is the only way to control the input. So for right now, if we test, if our input is off, we are expected to get an on. So if input is off, we're supposed to get an on, but we get an off. So probably we need to use an inverter. Okay, so if the input is on, or if the input is off, we're supposed to get an output of on. So the first condition is okay. And if we test the first condition, it's successful. And then we're told that if the input is on, we are supposed to get an on as well. So let's see if we do get an on. And unfortunately, we don't get an on. So it means there's probably some issue. So how can we fix this issue? Okay, maybe let's have a branch whereby the signal is always on. Oh yeah, and we can order that since we need the signal to be always on. So if the signal is off, the inverter turns it to off. If the signal is off, the inverter turns to on. And since there is an OR gate between this route and this other route, as we saw, the OR gate compares two inputs. And if either of the input is on, then the whole output is on. So we see that we have two inputs, which we picked an input branch from here to the OR gate, and also the one from here through the inverter to the OR gate. So whichever the condition, the OR gate is going to have one signal that is on, and that results to the output being always on. So if the input is off, we have our output as on. And even still, if I turn on the input, then the signal uses this other route and is able to satisfy the condition for OR, and therefore we have our signal on. So this is the circuit for always on, and if we test that, it's successful. So it says that this level unlocks your first manual page. This one is important to make sure you understand it. Okay, let's see. There's De Morgan's law. The truth table of the fundamental gates are symmetric. Okay, you can convert between them by inverting the input. Vertical arrows. Oh, that means if I have an OR and just invert the input, the input. If I have an OR and use this NOT gate before the OR, I get an AND gate. If that's what I'm getting. Or inverting the outputs for the horizontal. Oh, okay. Nice, I get it. So if you have an OR gate and you invert the two inputs before they reach the OR gate, you get an AND gate. And if you have an NOR gate and still you invert the inputs before it reaches the NOR gate, you get an AND gate. And if you have an OR gate and invert the output, you get a NOR gate, which is an OR NOT. As you remember from the previous thing, we had an OR, and then the circle thing is supposed to represent this, which is a NOT or an inverter. So from doing that, you get a NOR. And if you have an AND gate and then you invert after the signal comes to here, the first input, second input without being inverted, and then we invert the output, then we get the AND gate. That's the De Morgan's law. Okay. Oh, okay. The horizontal ones are a bit clear to me, but the vertical ones, I think I need to revisit that. But the note says that you can get from any basic gate to any other. At most, you have to NOT both inputs and outputs. Okay. You can go between OR and NOR. Okay, it's essentially the same thing we're talking about. So yeah, so we'll refer from this manual if we get stuck at any point in our learning. So yeah, and now we have an always on, which we constructed, which is this, and we have an always off. Okay, onward. The next one is second tick. Okay. As you know, these tests culminate in building a functional computer. So all we're doing is just build up to understanding how a computer is designed. Okay. Species that are capable of finishing are considered sentient by law. Okay. This is the main reason we don't eat you afterwards. Okay. So output a green, which is an on the second tick. From what I know, a computer has to run through ticks. A tick is essentially like a pulse, which is similar to a heartbeat. Let me say a heartbeat. So on a heartbeat, we have the heart pumping blood to the body, and it's kind of the same way. If the heart, as we know, if the heart stops to pump blood for some time, you will probably have some dizziness of some kind and just probably black out. And if you go for long, that's an issue. You can have brain damage and other kinds of things, and even death. But it's the same way as the computer. The computer has to function using this tick. It's like there has to be something that's causing some things to move, right? So in this case, one tick is able to navigate these signals up to a point, the next tick to another point, and that's how a computer is able to function. If a computer has a low tick rate, that's what I guess from computers you've heard of a CPU clock cycle. Most of them, I guess, are 2.5 gigahertz and onwards. That's usually representing the frequency at which things are able to move. It's directly related to this tick that we're talking about. And that without a tick, usually, I guess in the final classes, we're going to see how a tick is generated by a clock to generate these pulses, which the faster they are, the more powerful the computer is. And if you have slow tick rate, that means your computer is going to run very slow. And that's why you have high-end kind of computers that run incredibly fast, big games and everything. But if you have just a simple CPU, you're not able to run some games since it's very laggy, right? So that's essentially what I know about a tick as we get into this. But let's see what this class introduces us to the tick as. So, okay, I didn't catch that. And we can just refer to what the level ones. Okay. Capable to finishing. Okay. This is the main reason. Okay. Or output green on the second tick only. Okay. That means that. Okay. Second tick. Confused. That means if we go next, we're supposed to get this. Okay. And next. Next was, okay. We're supposed to get a green on this second. Oh, okay. Okay, let's look at this truth table. As it says, yeah, it's easier to look at the truth table than to try and figure other things out. If we have an input of off, right now we have two inputs, this, which is this, and this, which is this. If we have both of them off, our desired output should be off. So yeah, we can probably use an OR gate. Let's just use an OR gate for a start and see the output as off. So that's correct. And it also says that if the input, the first input is green, which is this, which green means on, we are supposed to still get an green, which is on, and that's okay. And if we go to our third input, it says that if we invert this, if we invert it, like this is on, this is off, and this is on, we're supposed to get a red, which means no signal. But we get this. And so if we get this, how do we make it off? And a way to make it off is to just invert. But we don't invert over here the whole output. We'll invert this route whereby this second input is on. And now if we start again, both of them are off, we get on. Okay. Okay, that's because of the OR gate. Let's change the OR gate and use a more strict gate, which is an AND gate. So if both of them are off, then the output is off. Okay, since both of them have to be the same, have to be green before the output of an AND gate is green. On, let me just use on. Yeah, it's on. And if the first input is green, is on, and the second input is off, we are supposed to get an on, which is okay in this case. And again, if the first output, the first input is off, and the second input is on, we're supposed to get an off, which is okay. And if both of them are on, we're supposed to still get an off. Okay, both of them are on, and yeah, we do get an on. So we have, if we test, the first signal is okay, second condition is okay, third is okay, fourth is okay. So basically you see that we can, just by using this gate, we can get any kinds of outputs that we desire, right? And as we can see, just if we can determine whatever output we want, then we're able to build a computer that does exactly what we want. So yeah, and onwards. Our next and probably final for this class should be XOR, right? So XOR is an exclusive OR gate. So let's just see what it talks about. Last level, you build a circuit that was on when we were at the second tick. Okay, this level, build a circuit that is on when we are at the second tick, or the third tick. Okay. So, okay, that's the condition. Right now it's, last time we just had these tickers on. And now we're told that both of these are on. So let's just start at constructing the previous one that we created. So we had two inputs, we had an AND gate, we had our outputs come through the gates, and that, and we also had our input, our second input inverted, and this satisfies just a green on this one, on this second tick. But now we also need to get a green, an on the third tick as well. So the third tick has our first input as off, and the output as on, but it's off. So that's where we should figure out how it's going to be. And okay, but we can see the only part of this circuit that is on is this part. So probably we need this part, but we're going to OR with this other output from this, so that we don't really affect the circuit, only affect when this is on. Let's see if it is going to work. So right now we have brute forced our way to getting the third tick as the input as off, on, then on. That's by brute force. So I hope it hasn't really broken anything, and so we have to test. Both of them are off. Our output is off. Okay. The first one, only the first one is on. Our output should be on. Our output is on because we don't really affect anything, and an OR gate doesn't really affect. If one signal is okay, then the whole thing is okay. And the third one is, if we invert, we are supposed to get the same. So if we turn this off and this on, now the signal does not take this route to the AND gate. It's because that is not going to work, because we have an inverter. It takes this other route to the OR gate, and it skips the AND gate, and we're able to meet that condition. And the final one, if both of them are true, we're supposed to get an off. So this is gonna fail, I'm sure. And we get an on. So it means that if this has to exclude this. Like, both of them cannot be the same signal. Okay, so let's go back here and okay. So if both of them are on, we need to invert the signal. Oh, okay. That means that if both of them are on, it means by just keeping this AND gate, we're defeating the last signal. So That means the OR cannot be here. Or it can be, but with another AND gate. Exclusive OR. Okay. Oh, okay. There's something that I learned on how to know how to construct this. Let me see. It's by looking at the output, where the output is on, and trying to construct a formula from there. Let me just find what the topic was, and you'll probably go and look at that. Yeah, it says that check XOR checks if the inputs are different. So, and fires the 1 only if inputs are different. If they're the same, it does not. It fires a 0. That's what an XOR does. Oh, it's called the whatever I was looking at, whereby we're supposed to construct a formula. It's called the Karnaugh. Is it the Karnaugh Map? Yeah, you should go and look at it. But it's going to help you. So in this case, we want to check that the XOR gate checks if the inputs are the same, and if they are the same, it turns it becomes off. It checks if the inputs are different, and if so, it fires. So we can't have inputs being the same. Okay, so I don't know if okay, let's start over on another one and see if we're able to do a proper XOR. So if the first input, okay, we have our first input, our second input, they should not match. That is our goal. So if we have an AND gate, that means that if they, for right now, they are the same. So since they are the same, our output should be off, and that's okay. Our inputs are different, are the same, and if they're different, that's when we fire a 1. But right now they're the same, so off. And if they are all true, they're the same still, we are supposed to fire a 0, right? So again, how do we do that? And if they are different, like this is different from this, we're supposed to get a true. So let's just take that signal from here to this OR gate, and make our it's becoming same as the previous one. So right now the first condition, if both of them are off, then the whole thing is off. If the first signal is on, then the output should be on. And if both they are inverted, the second one is on, we are supposed to still get an on. So probably let's just pick another OR gate and do the same kind of routing we did on top, which is pick the signal, move with it to here, and also pick from the AND gate and connect over here, then also OR them. Let's see how it goes. And we pick our output. Okay, that means that again the two are off, we get an off. The first one is on, we get an on which is okay. They are inverted, which means the second input becomes on, and now the signal can use the other routes. And finally, both of them are on. Then it becomes off. That's where I don't get it. Okay, but this is becoming tough. According to the Karnaugh Map, we're supposed to get, if input A, let's say input A is equals to A, input 1 is equals to A, input 2 is equals to B. That means that, and we need that A and B, and our outputs, we expect that 0, 0, the output becomes 0, 0, 0, 0, 1, 1, 0, 1, 1. The first output is 0, which is this. Second one, we expect a 1. The third one, we expect a 1. And the last one, we expect a 0. So if we were to construct a formula, we look at this, where we have green, where we have output as 1 and output as 1, and it's these two of them, and try to derive a formula from there. So it says A naught, which means it's A naught. A A inverted, and this is times, which is same as and, B, which is, this is Z. This is what we are looking at. It's A naught input. We've said input 1 is A, input 2 is B. So A naught times B, which is true, plus is an OR gate. This other one where our output is green, it becomes A, since A is green, and B times B naught. Then that is the formula that we need to construct the logic gate. So again, let's not delete it and just do another test 3. Yeah, I know the Karnaugh map because I had studied before, but you can go and look at it and let's see if it's able to construct for us what we need. So we say A, this is A, and we are told the formula tells us A bar, which means A bar, by this, doing this, by bar I mean inverted. So A bar and plus B, that means that signal and this signal B, which is not inverted, and we need to times them. So and is times, and also pick A, which is A. Guess let's move this a bit, and then again A and B. This is B. By B I mean input 2, but it's not B. We need to invert the B, so B naught. We can take this, and now we have B naught, and then we're supposed to times them, which times multiplication is just an AND gate, and we can multiply them, which is similar to an AND gate. And finally we have this, the first one and the second one, and then we have to add them, which is OR. Again, I know this by looking at the cog, is it the let me see, the Karnaugh map, and yeah, you should go look at it. I guess I'm gonna link it in the description, where I did study about the Karnaugh map. And now the output, we're supposed to add it, and by doing this output, without a lot of doubt, should be able to satisfy this. First is okay, second condition is okay, third one is also okay, and the final one is okay. The good thing about mathematics is that it's kind of straightforward, and it's able to help you be able to reach a certain goal almost every other time without a lot of issues. And I guess the Karnaugh map does the same for us. I'm gonna link it in the descriptions. Go and look at it. And yeah, that should be all for our class today. Our next class should be on it's a bigger OR gate and a bigger AND gate. This should be easy since we already know how an AND gate is. And yeah, see you in the next class. Bye.